So this is our first numerical to be solved. It goes like this. An electron beam is accelerated from rest through a potential difference of 200 volt. Calculate the associated wavelength. It means calculate the associated de Broglie wavelength here. Okay. So when you look at this numerical, the data already given was the potential difference of 200 volt, and it asks to calculate the de Broglie wavelength. You know the expression for de Broglie wavelength, lambda equal to h by p, where p is root of 2me, that is root of 2me. In place of e, we will take ev, that is capital E is equal to ev, that is kinetic energy is equal to the charge on the electron and capital V, voltage. Therefore, the de Broglie wavelength formula, that is lambda is equal to h by root of 2m ev. Okay, where h is as usual, it is Planck's constant, 6.626 into 10 to the power of minus 34 divided by root of 2. M is mass of the electron. You are here the electron beam, isn't it? Therefore, it is the mass of the electron should be considered. The charge on the electron is 1.602 exponent of minus 19. It is accelerated under the potential of 200 volts. Therefore, it is 200. Do this calculation, you will get 0.86 angstroms. That is this. Find the de Broglie wavelength of an electron accelerated through a potential difference of 182. Find the de Broglie wavelength of an electron accelerated through a potential difference of 182 volts, 182 volts, and 1 kg of object. Any other mass of 1 kg is considered here. Here we have considered two objects. One is electron, another one is a 1 kg of mass, are moving with a speed of 1 meter per second. Both are moving at speeds of 1 meter per second. Compare the results and explain the wave nature of matter is not apparent in daily observation. So here what are you are doing that you are measuring the de Broglie wavelength of electron and the de Broglie wavelength of a matter of 1 kg mass, and this 1 kg mass is moving at the speed of 1 meter per second, and if this is so, calculate the de Broglie wavelength. So to get the de Broglie wavelength of an electron, the formula you know as usual, it is accelerated under potential of 182. Therefore, the equation, the formula becomes the lambda is equal to h by root of 2m ev. You already seen in the previous one. H is Planck's constant, m is mass of the electron 9.1 10 to the minus 31, and the charge on it is 1.0602 minus that is exponent minus 19, and voltage the same similar to the earlier one. Instead there it was some around 220 something, it is 182, and the wavelength is found to be 0.91 angstroms. If you calculate the de Broglie wavelength associated with 1 kg of object, then you can straight away use the formula lambda equal to h by p. So p is momentum, the mass into velocity. So if you substitute the mass as 1 kg and velocity is 1 meter, and the numerator is the Planck's constant, the answer is equal to the value of the Planck's constant. Here you will get the wavelength of order 10 to the power minus 34, and with respect to an electron it is of the order of 10 to the minus 10. So look at the difference. If you are working with microscopic particles, the wavelengths can be measured, it's around angstroms, so 0.91 angstroms. It is really an measurable quantity and physically measurable quantity, and as well it is an observable quantity, is physically an observable value. But look at the wavelength associated with the 1 kg of mass, it gives you around 6.626 into 10 to the power minus 34. The order is 10 to the power minus 34. Such a very small of wavelength cannot be noticed physically. So it becomes physically an observable quantity. If you apply the de Broglie wave, this wavelengths to with respect to macroscopic particles. The overall conclusion is that if you are applying this quantum mechanics to a macroscopic particle in finding its wavelength, etc., the values you will get finally they are very very small, unnoticeable, noticeable. You don't see the difference of such a smaller value. It cannot be noticed, cannot be felt in the physical world. Okay, so it is not possible to observe physically. That is the conclusion you can get from this numericals. So now in the third one, calculate the de Broglie wavelength associated with a proton. See, I told you that we are dealing in quantum mechanics. Whenever you measure the wavelength, de Broglie wavelength, etc., certainly we are dealing with the microscopic particles. If you apply it for a macroscopic particles, you have seen in the previous numericals, the values you will get ultimately they are very very negligible, minimum, and you cannot expect to be an observable physically an observable quantity. Okay, so now we have another particle like proton. It is much heavier than the electron, you know that. So now calculate the de Broglie wavelength associated with a proton moving at a velocity is 1/20th of the velocity of light. So velocity of the proton here is 1/20th of c, where c is the velocity of light. So first you calculate the velocity, that is 1/20th of c, that is 1/20th multiplied by with a substitute for c, it is 3 lakh kilometer per second. So the answer, I mean, velocity becomes 1.5 into 10 to the power 7 meter per second. So the velocity of the proton here, which is moving if is at 1/20th of velocity of light, is equal to 1.57 into 10 to the power of 7 meter per second. This is the velocity now. And here mass of the proton, you assume the mass of the proton is equal to 1.67 into 10 to the power minus 27 kg. Substitute into the equation, and that is lambda equal to h by mv. H as usual Planck's constant. Mass is 1.67 into 10 to the minus 27. That is multiplied by the velocity 1.5 into 10 to the power of 7. If you do this, you will get the order of 10 to the power minus 14, 2.64 into 10 to the power minus 14. You know that angstroms are around 10 to the minus 10. It is now it is an extra order of 10 to the power 4. So all these values are can be physically measured and under in quantum mechanics. It is an observed quantity. It is the wavelength of the proton. It is printed there is electron. You correct it. It is the wavelength of the proton. Find the energy of the neutron in units of electron volt, whose de Broglie wavelength is 1 angstrom. So the numerical here, the mass of the neutron is given. So given the mass of the neutron and the de Broglie wavelength is equal to 1 angstrom, calculate the energy. What is its probable energy? So use the same formula, that is lambda equal to h by mv, that is equal to h by root of 2me. You know how we will get this. So now we square, and on left hand side and right hand side, lambda square is equal to h square by root of 2me. Now sorry, root goes, lambda square is equal to h square by 2me. So push e to the other side, so it is to the left side, e equal to h square by 2m lambda square. So this e is the energy of the neutron, which is moving as a wave having a de Broglie wavelength 1 angstrom. As usual, you substitute the Planck's constant divided by, that is square of the Planck's constant divided by twice of the mass of the neutron, 2 into 1.674 exponent of minus 27, and it is 1 angstrom. So the wavelength, de Broglie wavelength 1 angstrom, square that. The answer is 0.813 milli electron volt. So this is the energy of the neutron is equal to 0.813 milli electron volt. An electron filled with helium is heated at 400 K. A beam of helium atoms emerges out of the enclosure. Calculate the de Broglie wavelength corresponding to the helium atoms, given the mass of the helium atom is 6.7 into 10 to the power of minus 27 kg. See here, it is kinetic theory of gases is considered, where energy of these helium atoms is given by T by 2 kT. You can note down the energy of the helium atoms in a kinetic theory of gases energy of these gas molecules is given by, write down, E, capital E is equal to 3 by 2, 3 divided by 2 K into T. E equal to 3 by 2 K into T, where K is the Boltzmann constant, T is the temperature. That is for lambda equal to H by P, that is equal to H by root of 2 ME, isn't it? So in place of E, you substitute 3 by 2 KT. So here, in place of E, you substitute 3 by 2 KT. So 2 in the denominator and the 2 there in the numeric, within the root gets cancels. So it is only lambda equal to H by root of 3 MKT. So the formula for that is the wavelength, de Broglie wavelength in this particular case is equal to H by root of 3 MKT. H, Planck's constant as usual, within the roots 3, that is the mass of the helium atom is given to be 6.7 into 10 to the minus 27 kg. K is Boltzmann constant 1.38 into 10 to the power minus 23, and the temperature is 400. You substitute these values and see that it will be around 0.63 angstroms